we're here to discuss how we can actually apply precision engineering principles to the complex clinical decisions of LVAD to transplant. And the core question is simple. Can we predict which patients truly thrive after this critical transition? We're moving beyond simple metrics to define what doing well actually means for these patients. And this requires a shift in how we approach risk stratification, moving from static historical data to dynamic real-time intelligence. And we believe the answer lies in everyday high-fidelity data and advanced modeling, creating a new standard for patient selection. But first, we must acknowledge the current limitations in predicting success. And the challenge is clear. We have a significant prediction gap in bridge-to-transplant or BTT outcomes, and current risk models are often broad, failing to capture individual patients' physiological trajectory, where we're often relying on data points that are too infrequently or too late to inform timely intervention. This lack of precision leads to suboptimal timing for listing and potentially misses the opportunity for pre-transplant optimization. And we need a system that acts like a digital cockpit, providing continuous high-resolution feedback to guide our clinical decisions. And this means defining success with more rigor than we technically do. So defining doing well requires us to look for beyond the 1 year survival rate. We must measure true functional recovery and quality of life. And we're focusing on metrics like freedom from major adverse cardiac events, sustained functional capacity, and freedom from hospitalization. But this is about achieving a high performance clinical outcome, not just clearing the lowest bar. By setting this high standard, we force our predictive models to be more sensitive and specific. And we need the right data streams to capture these nuanced outcomes. So the HeartMate 3 device provides an unprecedented window into patients' real-time physiology. It's our primary source of high-fidelity telemetry. This isn't just pump speed. We're capturing continuous flow, power consumption, and pulsatility index, which are direct surrogates for cardiac performance and vascular compliance. And this continuous stream of data allows us to monitor the patient's physiological state minute by minute, identifying subtle shifts that precede clinical deterioration. This real-time data is the fuel for our engineered intelligence framework. We call this approach the digital twin framework, and that's the core of our engineered intelligence platform. The digital twin is a high-fidelity virtual replica of individual patient's cardiovascular system, which continuously updated by the HeartMate 3 telemetry. This framework allows us to run complex simulations or in silico trials to test various clinical scenarios and predict the patient's response to intervention. It transforms raw data into actionable foresight, allowing us to participate or anticipate outcomes before they manifest clinically. This is the precision engineering we bring to clinical care. The in silico trial is where we move from a theoretical digital twin to a high-performance virtual cohort. This is the precision engineering of clinical research, reducing the need for costly, time-consuming physical trials. We simulate thousands of patient profiles against new treatment protocols, identify optimal outcomes before a single dose is even administered or a single change made to the device. This virtual environment allows us to rapidly iterate and refine, much like testing a new engine design in a digital cockpit. We are compressing years of traditional research into months, delivering validated insights with unprecedented speed and rigor. This rigorous testing environment is only possible because of the evolutionary engine we've built. And our engineered intelligence is not static. It's an evolutionary engine, constantly refining its own code. This is the core mechanism that drives our predictive power, adapting to new data streams and clinical feedback loops. We use a genetic coding approach, where successful algorithms are selected and combined, creating a helix of ever-improving performance. This ensures our models never become brittle or outdated, maintaining peak performance under all conditions. It's the difference between a fixed system and one that learns and optimizes itself in real time. This self-optimizing engine is what powers our next major clinical tool, the Chi LVAD Bridge Score. So this Chi LVAD Bridge Score is our 100-point risk stratification tool, providing clinicians with an immediate, precise assessment of patient suitability. This score moves beyond traditional metrics. It integrates hundreds of variables to deliver a single actionable number. Think of it as a digital cockpit display for complex clinical decisions, giving you total situational awareness. It allows for proactive intervention and personalized treatment pathways. It maximizes the probability of a successful bridge transplant. But a powerful score is useless if we can't trust it, which brings us to the critical concept of validation. We're moving from a black box to a glass box through a process we call adversarial validation. Trust in AI is built on transparency, and we achieve this by actively trying to break our own models. We use adversarial networks to challenge the score predictions, forcing the system to expose and correct its biases and blind spots. This rigorous high-stakes testing ensures that every prediction is robust, explainable, and clinically defensible. It is the final quality check, ensuring our precision engineering meets the highest standards of safety and efficacy. This validated intelligence is the foundation for our future roadmap. So between 2026 and 2028, our roadmap outlines the shift from a reactive clinical model to a truly predictive one. We are scaling these validated tools across the entire patient journey, from initial diagnosis to postoperative care. The goal is to embed engineered intelligence into every critical decision point, driving down variability and improving outcomes across the board. This roadmap is about delivering on the promise of precision medicine at scale, transforming clinical practice through rigorous, high performance AI. This is the future we're building, and we'll probably invite you to drive it with us. Thank you.